Hello everyone, welcome to our class, the brachistochrone problem. In mathematics and physics, a brachistochrone curve from ancient Greek, meaning shortest time, or curve of fastest descent, is the one lying on the plane between point A and the lower point B, where B is not directly below A, on which a bead slides fractionless under the influence of uniform gravitational field to a given end point in the shortest time. The problem was posed by Johann Bernoulli in 1696. Bernoulli posed this path of fastest descent problem to challenge the mathematicians of Europe and used his solution to demonstrate the power of Leibniz calculus as well as his own ingenuity. I, Johann Bernoulli, address the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem, whose possible solution will bestow fame and remain as a lasting monument. Following the example cited by Pascal, Fermat, etc., I hope to gain the gratitude of the whole scientific community by placing before the finest mathematicians of our time a problem which will last their masters and the strength of their intellect. If someone communicates to me the solution of the proposed problem, I shall publicly declare him words of praise. This is the quote from Johann Bernoulli. In addition to Johann Bernoulli, solutions were also obtained from Newton, Leibniz, Johann's brother Jacob Bernoulli, and L'Hopital. At the time, there was an ongoing controversy ranging from whether Newton or Leibniz had been the first to invent calculus. An advocate of the methods of Leibniz, Bernoulli did not believe Newton would be able to solve the problem using his methods. Bernoulli attempted to embarrass Newton by sending him the problem. However, Newton did solve it. Newton submitted his solution anonymously, presumably to avoid more controversy. Bernoulli's ingenious solution starts, interestingly enough, with Snell's law of refraction. He begins by considering the stratified medium in this figure, where an object travels with velocity v1, v2, v3 in the various layers, just like this figure. By repeatedly applying Snell's law, he concluded that the fastest parts must satisfy with this, such as sin c1 over v1 equals sin c2 over v2 equals sin c3 over v3, and so on. In other words, the ratio of the sine of the angle that the curve makes with the vertical and the speed remains constant along these fastest parts. If we think of continuously changing medium as stratified into infinitesimal layers and extend Snell's law to an object whose speed is constantly changing, then along the fastest part, the ratio of the sine of the angle that the curve's tangent makes with the vertical alpha and the speed v must remain constant. That means sin alpha over v equals c. If we include x's and p denotes the position of the bead at a particular time, then we have the following picture. This one. In the picture, s denotes the length that the bead has traveled down to point P. That is, the arc length of the curve from the origin to that point. And a denotes the tangential component of the acceleration due to the gravity g. Since the bead travels only under the influence of gravity, then the derivative of v with respect to t equals a. So a over g equals dy ds. Always say a equals g times the derivative of y with respect to s. Moreover, since acceleration is a derivative of velocity, this is the same as the derivative of v with respect to t equals g times the derivative of y with respect to s. Now observe that by chain rule that dv dt equals dv ds times ds dt. The physical interpretation of this formula is that velocity will depend on s. That is, how far down the wire the bead has moved. But that the distance traveled will depend on how much time has elapsed. Therefore, the derivative of v times the derivative of s equals g times the derivative of y. Always say ds dt times dv ds equals g dy ds. And since the derivative of s with respect to t equals v, so we have this. Now we integrate both sides with respect to s, then we'll get this one. And integrating this, we can get that v squared over 2 equals g times y. Just now we solved the problem with modern notation. We'll use hand to calculus that in the differential notation of Leibniz. With Leibniz calculus, the chain rule looks like cancelling expression in the top and the bottom of fraction, such as dv ds times ds dt is equal to dv over dt. This is because for 18th century mathematicians, this is exactly what it was. After finding v squared over 2 equals gy, then with the differential equation and the calculus of variation, you can find the equation of these parts of fairest descent as x equals r times theta minus sine theta, y equals r times 1 minus cosine theta. From this picture, you can see that although the curve of fairest descent isn't the shortest curve, it's the fastest. This is because the acceleration, when it is released, depends on the steepness of the descent. And along this curve, it builds up velocity much more quickly than it does along a straight line. Alright, today we discussed the fastest descent curve. And this is a famous problem in the history. That's all for this section. Thank you.